It's a pleasure and an honor. I am particularly attached to Costa Rica for a number of reasons. My best friends probably was there for a long time, and I visited several times, have dear friends there. I think it's a fantastic country for a number of reasons. I wish I was there in person. I am also happy to be in this conference where, as Lorenzo said, the interplay between philosophy and science, it's looked at, an interplay which I think is vital, needed for both disciplines, without which both disciplines, I think, risk to lose and become more sterile. The work of my life has been in quantum gravity, trying to figure out quantum gravity. And for figuring out quantum gravity, there are two major conceptual issues to address. One is time, and we just heard from Kasia, and this is a theme which is very, has always been very dear to my work, my intellectual work. I have found extremely interesting the conference of Kasia this morning. It's extremely illuminating for me. And the second is quantum mechanics, and I'm going to talk about quantum mechanics. This is a topic of my presentation. Again, the reason I've been interested in quantum mechanics is because to do quantum gravity, we need as much clarity as possible on time, space-time, and also on quantum mechanics. And this is why the reflection of quantum mechanics has followed me all my life. My last book, Helgoland, is about quantum mechanics, and it presents, and this is what also I'm going to do here, the view I have about quantum mechanics, which and the view I find more interesting about quantum mechanics, which is a relational view about quantum mechanics. Let me share my slides here. Sorry, just 1 second. Yeah, here it is. And share screen, advance the portion of screen, share. Just kill this one, which is not the right one, and put it in center. Is that okay? Do you see it right? Can you just, Lorenzo, can you just give me a sign that the voice is fine and the... Is that all fine? Are you okay? Good. So this is the title of my talk, and that's what I'm going to talk about: trying to make sense of quantum physics, what we have learned about the world about quantum physics, and in particular focus on the relational interpretation. And what I'm going to do is first try to frame very rapidly the problem of quantum mechanics. I'm sure that in the audience, there are people who know this well, but let me try to present it in one way, because as usual, one of the problems in addressing a problem is finding what exactly the problem is, formulating it. So I'll try to give my take on it and say why, in this context, the relation between science and philosophy plays a role. And then I will go to relational quantum mechanics. I'll try to explain what it is and why it might represent one way of addressing the interpretation of quantum mechanics. And I will zoom in on some historical consideration about it, and I will close, which is sort of the tentative main message of the talk, which is to forget the wave function, not think about the world in terms of a wave function. But let me start from the beginning, super rapidly. Quantum physics is, I would say, fantastically successful. It's probably the best scientific theory we have ever, because it has never been wrong. It has predicted spectacular things. And more than that, we have no indication of its limits. We have other super good theories in physics, but we think we know where they are supposed to go wrong. Quantum mechanics, we don't know where it goes wrong. Maybe it will, but for the moment, we have no indication that it should break down somewhere. It has given spectacular applications, results, predictions. It has allowed us to understand the basic of chemistry, how the sun works, and so on and so forth. Okay, so far so good, but it's truly incomprehensible if you think it's carefully. And the way it's presented in the books, usually, it generally makes no sense at all. The way it's presented in the book is that the theory is about what we see when we look, and not about what happens there. So the theory is formulated in terms of physical systems, quantum systems, which could be the sun, could be a molecule, could be an atom, could be a radioactive nucleus, could be a chip in the computer, a little transistor in solid-state physics in the computer, or formulation of a galaxy in the star. The whole system which are treated quantum mechanically. So there's a system, and here I draw the system in just the symbol of an atom, which is a typical quantum system. And the theory doesn't tell us what happened in the atom at all, but it tells what happens when the atom interacts with us. So it's like, it is formulated as if nature cared whether we're looking or not. But we don't believe that nature cares whether we're looking or not. In fact, I don't believe so. I think that I'm a piece of nature like any other, and that a description of nature, of course, might take into account, which I'm giving it sort of from the inside, for being a piece of nature, but not that I'm special in physical terms in some sense. That's a problem. In a couple of slides, I will zoom it in a little bit more clear distinction. But I want to immediately say what are the direction of thinking which are common in physics nowadays about this problem, which I've grouped into 6 main directions. Each one sort of is declined in different manners, and there are others. I don't want to say these are all there is, but these are by far the directions which are more discussed. And the relational one, which is the third, which I want to discuss, is it's emphasized in blue. Among practicing physicists, the Copenhagen view is it's usual. It works very well, and it's the idea that a quantum system, here's a quantum system, take a value, become real, so to say. Their properties become the real, where they interact with the measuring apparatus, with obvious sort of an obvious sense of incompleteness in this story. Stronger in that direction, it's quite popular in recent years. A stronger version of this, where the theory is just about what an agent, here is it's man looking, can say about the world. So it's only about things being realized when they interact with the agent. So it's all about agent knowledge, not about the world itself. I'll skip relational quantum mechanics for a moment and jump to the other sort of 3 ways of making sense of quantum theory, which is that the theory really describe a wave function or a quantum state, which is all there is to say about the quantum system, independently of any observer or any measuring apparatus. And this comes in 3 varieties, I would say. The many-world interpretation, which philosophers at Oxford love, and some cosmologists and theoretical physicists love, in which there's also only the wave function. And out of that, you should come out the observations, and out of that we should extract the strange observations related to an observer that the theory predicts. An alternative is to imagine this wave function, but also some real facts of the world, where the particle is, what is happening at some point. Both these views, the many-world and the hidden variables, add a lot of sort of ontology, if I may, to the picture of the world, which is simple quantum mechanics. Many worlds requires us to think that there are many copies of ourselves that are seeing different things, and hidden variables, as the name indicates, assumes that there are some physical variables which are hidden in principle, which are inaccessible to us. By adding all that, one construct in some sense classical, in some sense closer to our previous classical intuition understanding of the world as a substance that evolved in some way. And the third possibility is that there is the the wave function, but there is some phenomenon not yet discovered. So this is the only view of quantum mechanics that requires to think that quantum mechanics is actually wrong. And it has to be, there's something we haven't discovered again. There is some actual physics that constantly changes the wave function by making the wave function collapse, namely making it being specific independently of an apparatus or a man. Let me make this all a little bit more concrete. This is a prototypical quantum experiment. We have an atom of uranium or whatever, which is radioactive. We have some detectors around, Geiger detectors, and the atom is radioactive. At some point, one detector clicks, meaning radiation has been detected. Now, the way we describe this in quantum mechanics is by thinking that there is a wave function, a wave inside the atom, which moves out, leaks out continuously and goes everywhere in space, right? That's what we do in our paper. That's what we're told to do at school. And at some point, these waves interact with the counters, but only one of them, and never more than one of them, reacts, and boom, the wave now it's concentrated on that particular detector. So it's like when there's a detection, something happens. But of course, the question is what is a detection? When is it that this happened? And you probably know a famous way of making this very visible, which is due to Schrödinger, who imagined a cat, the famous Schrödinger cat, would interact with the quantum system, and in the moment of the interaction, something happens. The quantum system gets a determinate value, because this is what I'll talk to do in quantum physics. But if I consider the cat itself a quantum system and interact with it later, then I have to think that the cat, it's really like the previous example, the wave function spread all over, is spread over two different positions, the cat that has detected one thing and the cat has detected the other thing. And if you think that the cat is a person, the usual language in philosophy is to call the outside one Wigner and the cat a Wigner friend, because of a famous article of Wigner about this situation. Then the Wigner friend sees something, because we all see something, but is also in a superposition of different configuration, having seen something and seeing the opposite. And that's, in the many worlds picture, for instance, you think that they're both real. So every time we see something, there is a copy of ourselves seeing something else. So these are the various ways in which, I'm back to these slides, this is resolved. But I think that something becomes real when you interact with an apparatus, a microscopic apparatus, with an agent, or by trying to make a complicated story, adding reality. I mean, nothing really happens, multiplication of observer configuration, and so on and so forth. Now, one may say, and this is a comment about philosophy of science, one may say, look, first of all the first 5 of these ways of viewing quantum mechanics actually never give different predictions. The last one does, but let me forget the last one, because they're experiment trying to check it. And for the moment, they have all given negative result. If they will give positive results, quantum mechanics needs to be corrected, we will think about. But for the moment, quantum mechanics is the best that shows the world. So let me look at the first 5. They're very different philosophically, extremely different philosophically, because I'm not going too much into slide, but they incline toward different philosophies: pragmatism, empiricism, even idealism, certain instrumentalism on the one hand, and a strong commitment to a strong version of realism, even deterministic realism in many world and hidden variables. Each one of this is coherent. It's not that they're wrong; they're all consistent, but they have a sort of a philosophical cost, so to say. Copenhagen requires us to not pose the question why the apparatus is not quantum mechanical. Cubism assumes a sort of agent as needed to think of nature. The many world interpretation, as I said, has hugely inflated the ontology in which there are copies of ourselves that see different things, and so on and so forth. So one may react as not in this audience, but among many of my colleagues, saying that philosophy is not of interest for physics, right? And my typical answer to that is that this reaction it's not new in the history of science. There are many examples. The most famous examples of all, I'm sure you know about it, in this when Copernicus published his major book, De Revolutionibus, which sort of jump-started the modern scientific revolution in the Renaissance. The preface written by Osianger made the point very strongly that to ask whether the sun is the center of the universe or the earth is the center of the universe is just philosophy of not interest for science, right? I'm not going to read it, but the preface, which was not written by Copernicus, of course, that was definitely not the view of Copernicus, says that the different hypotheses need not to be true or even probable. The Earth going around of the sun needs not to be true, not even probable. And if you think carefully, is that an empirical question, that the Earth moves? It's not an empirical question, right? There's no way whatsoever to measure if the Earth is the center of the universe or is not the center of the universe. It's not an empirical question. I mean, if you want to think that the Earth is the center of the universe, there's no observation that contradicts us. So what's the point? The point is that by rethinking conceptually what it means to move, by allowing this Earth to move, by reorganizing the conceptual structure in which you don't separate Earth and the other heavenly body, but you separate stars and planets and satellites, you have a different conceptualization, which work fantastically better for understanding the world. So much so that it allows Huygens, Kepler, Newton, Galileo, and so on and so forth. So I guess the point I'm trying to make here is that science is definitely not just about, having equations that spit up numbers that we compare with what we measure. That's not science. That's a tool for science. Science is not just about strict verificationalism or falsificationalism as a la Popper. Science is about devising a conceptual structure which is useful for understanding the world. And there are clear moments in which this is confused, like just after just after Copernicus, or just after Maxwell, when people were conceptually confused about how to think about this Maxwell novelty, Faraday-Maxwell novelty, which are the fields. I mean, do we have to think of some effective description of some particle, ether moving there, or do we have to think about taking them as just our best description of what is real, so on and so forth? These are not non-scientific questions. These are questions at the core of science that don't have a strict empirical answer. You cannot verify or falsify an answer to this question directly, but they're deeply scientific because they regard the best way for conceptualizing nature. So the distinction between the different perspective is not non-scientific, as is often put, but it's at the core of science. And then the argument is not what is wrong. The argument is what is the best effective way of describing the world. Let me jump ahead to this slide here. Richard Feynman, who is a great scientist and with a remarkable intellectual clarity, said that one of the amazing aspects of nature is a variety of interpretation schemes it admits. So what to do with the rest? So to discuss about underdetermination of the theories or things like that? No, he says every theoretical physicist who's any good knows 6 or 7 different theoretical representations of exactly the same physics. So is that being relativist deeply? No. Why? He must keep the sentence any good, must keep there in his head or her head, because one of them may turn out to be the fruitful one. So one of them is better, is definitely better. And my job is to do quantum gravity. I have to keep them keep all this interpretation in mind, but try to see which one is better for understanding nature better, for going ahead in the interpretation, in understanding of nature. So let me get to the, how much time I've used? Good, plenty of time. Let me get to relational quantum mechanics, which is the blue one here, which I've not discussed, and which I'm going to illustrate. Oops, sorry. Which I'm going to illustrate. I want to start from, to introduce the main idea of relational quantum mechanics by discussing, I work at like a Filosofía, by discussing a phrase by, a sentence written by Niels Bohr, which is one of the deepest thinkers of quantum mechanics. So Niels Bohr writes, and I want to discuss this because I think a careful discussion of it clarifies enormously. Niels Bohr writes, in classical physics, the interaction between an object and the measuring apparatus can be overlooked. In quantum physics, the interaction is an inseparable part of the phenomenon. Therefore, the ambiguous description of quantum phenomena is required in principle to include a description of all the relevant aspects of the experimental arrangement. Now, this is the core of quantum physics, but is also deeply misleading because 100 years have passed since Niels Bohr. When he was writing these things, most of the quantum science was in a laboratory with apparata. Now we know that quantum physics is good for the star, the galaxies, everywhere, and it's actually the foundation of our current physics. So we have to say the same, to understand the same thing without reference to apparatuses and without reference to experimental arrangement. And here is the way to do so. We just have to rewrite his sentence in a less anthropocentric manner. And this is my rewriting of Niels Bohr's phrase. In classical physics, the properties on any object are determined irrespectively from the interaction between these objects and others, not necessarily apparatus, whatever is interacting with. So quantum physics, what it is the discovery that interactions with apparatuses or any other object are an inseparable aspect of the properties of an object. The phenomena, it's what phenomena are about. So therefore, the ambiguous description of any object requires the inclusion of all the objects involved in the interaction in which the object manifests itself. So the idea is to forget observation, forget humans, apparata, macroscopic, anything like that, and just focus on interaction, and forget the actual measurement and think about relations established when things interact. So this is the core of the relational idea, two ideas, two key ideas, and then some technical things which, given the audience, I don't want to go too much into it. But the central idea is the following. Physical systems have properties, but the properties don't describe the system as they are by themselves. What the property of a system is a description of what happens in their interactions. Properties exist at interactions. So therefore, the properties have values at interaction, not necessarily before, independently from the interaction. There is no meaning of giving a property to attributing a property to a system outside interaction, because the property is a description of what happened in interaction. And second, crucially, this is where relational interpretation takes its names, the properties are relative to the interacting systems. So we shouldn't say the particle has got to that point. We should say with respect to that detector or set of detectors, the particles go to that point. We shouldn't say the quantum system has affected the cat. We should say with respect to the cat, the quantum system has a property, but not necessarily for the person outside. So a property with respect to Wigner friend is not necessarily a property with respect to Wigner outside the box. And technically, this step here is the key one. The probability, quantum mechanics give probability. Probability is that A happened given B. But we have to interpret these probabilities, which the formalist, the mathematical formalist gives, only when A and B refer to the same interacting systems. And the probability computed as property with respect to a system S prime given property with respect to a system S different from S prime have no meaning in general. Okay, this is not, we should not read the formalism as saying that this is significative. The transitional amplitude is significative only as interpreted as a property with respect to a given system. So in the Schrödinger cat, the atom has a certain property with respect to the cat, but this does not imply or should not be used to compute interactions between the cat on the atom and some external physical systems, because a property relative to the cat has no bearing with a property with respect to a physical system. So it's not that the cat is in superposition or anything like that. It's that properties are real, concrete, part of the ontology of the world, realized at interactions, and their probabilistic relations don't jump from one observer to the other. In a sense, the fact that the property of the atom, say the spin of the atom was up or whatever, is relatively to the cat. And this way of putting things, fact are relative to physical systems, has got even to the experimental world. Here is an article that says experimental rejection of observer independence in the quantum world. So facts are relative, facts are deeply relative, in the sense that I said properties describe interactions, and they are relative to the interacting systems. So this is the sort of summary or total complete exposition of the relational interpretation of quantum mechanics. First is the notion of system, namely the world can be decomposed, in fact, in many alternatives ways. That's the beauty of the story. I mean, that it works whatever the composition of the world we make. We take the world, we break it in pieces, the sun, the earth, the moon, me, you, the cat, the atom, another atom, a molecule, another molecule. We can break it into systems in arbitrary ways. And this system interact, okay? The point is about the interaction between the system. What we describe is interaction between the system. Now, each system can be characterized by a set of variables. So mathematically, it's an algebra of variables, A1, AN, but these do not represent how the system is. They represent what the system does to another system in the moment of interactions. So it's something that pertains to the interaction. Outside this context, the properties are not determinate. We may assign a system a property, meaning that we expect that when it will interact, this property will show up. And in the classical domain, this can be done forgetting about detail and relationalism because quantum phenomena are washed out. But by themselves, properties only refer to interactions. These variables, therefore, take value only at interaction, and the value are relative to the interacting system. In addition, precisely because the variables form an algebra, what the theory predict is that they can only take certain values, discreteness of quantum mechanics. So the algebra, the value of a system determines a set of values that some property can have. The energy can have only these values. This is what the theory predict. The angular momentum can have only these values. So the formalism of quantum mechanics give the probabilities given certain values of some system relative to a system to compute the probability amplitude, the probabilities of other values of other variables of the same system relative to the same system. And finally, it can be shown, and it can be shown technically, that because of the coherence, because of the fact that when you have many degrees of freedom, you don't see interference anymore. Quantum interference gets washed out. Somehow you don't see quantum phenomena anymore. This labeling of properties by systems, by the system that are in the interaction, participating in the interaction where they come out, becomes irrelevant. So this can be shown technically that once you go to many degrees of freedom, having to remember which quantity is relatively to what becomes irrelevant because quantum properties are not there anymore. A few comments before moving toward the end. This was the core presentation of relational quantum mechanics. and because and before some sort of a historical and general comment that I will close by. First of all, I've never mentioned the wave function. And so what is a wave function? What is this wave that goes around? Do we have to think that in the world, in the actual world, there is this waving, and then make up a complicated story of connecting this waving with the fact that what we see is one and only one detector to interact? I think that the answer is a resounding no. Namely, the wave function is to be interpreted epistemically, in the relational interpretation. It's a wonderful tool. But it's a tool for calculation. And in fact, the classical limit of the wave function is the Hamilton-Jacobi function, for those of you who know classical mechanics, which nobody would ever dream of interpreting realistically. The Hamilton-Jacobi function is a tool for calculation. It's not that there is some, it's like the weather forecast or the prediction of the horses races. So it's a tool for saying what we may expect on the basis of current knowledge, what is happening in the future. Is a way of coding past observations, not something which is out there. First point. Second point, there are no special observers. Consciousness, human beings, macroscopic system, apparata play no special roles. Agents, I think, in interpreting nature. Not because they're not special. We are special, and there is a huge amount of scientific and philosophical work trying to understand us, ourselves. Super interesting, but that's not what physics is about. What physics is about understanding what happened in nature when we're not there. And for that, we don't need the notion of agent or subject of knowledge. We should be careful. We should sort of detect in our formalism what depends on the fact that there's an observer, but not pretend that nature knows whether there's observer or not when things happen. Now, the problem of quantum mechanics has often been presented as a tension between the unitary evolution and wave function collapse. And in relational quantum mechanics, this is resolved by essentially not interpreting the wave function realistically, so interpreting the wave function epistemically. So what the theory is about is values of quantities, and the unitary evolution is our calculation of the probability distribution at some time, given some information at some other time, provided that the system is isolated. So unitary evolution is a description of what to expect when the system is isolated. But of course, it's not going to work when something is actually realized in nature, and the variables take value. So it's since this is relative to one observer, the evolution is unitary. Relative to the other observer, there's a collapse. Remember, relative to the cat, the Schrödinger wave function of the atom collapses. Relatively to the external observer, it doesn't. But not because there is a strange tension to resolve, because these are two different systems. We're talking about two different sets of quantities. Now, today, in some places, quantum mechanics is introducing the Schrödinger wave function. But that's, I think, very misleading. And that's the source of the confusion. Quantum mechanics was not born by Schrödinger in 26 with the wave function. It was born by Heisenberg, Born, Dirac, Jordan the year before, in 25. Full quantum mechanics existed before the wave function, before the quantum state. And in that formulation, which I find extremely more clear, quantum mechanics is about systems, about variables. It has the same equations as classical theory plus one, which is xp minus bx is IH bar. So the only discovery, sort of, the atomic bomb, the lasers, the foundation of the Mendeleev table, quantum teleportations, quantum computers, they're all a consequence of the single equation xp minus bx equal IH bar, which says that variables don't commute and therefore have a spectrum, therefore is discrete, therefore we can compute probability amplitudes, therefore, okay? So the formula of quantum mechanics is like classical mechanics, plus understanding that at small scale, because h bar is small, classical variables don't commute, and we know how they don't commute, okay? No state, no evolution, no evolving wave function, no continuity. This is all about discreteness. As Max Born had clear in 1925, quantum mechanics is about a sort of a flash ontology of discrete events in the world, not about continuity. And the confusion is taking the wave function too seriously. And that's the origin of the confusion. And so the culpable is Schrödinger, if you want. But Schrödinger himself, one of the deepest thinkers of quantum mechanics, completely gave up the idea of continuity. This is a text by Schrödinger late. He says the inventors of wave mechanics himself indulged for some times in the full hope that they had paved the way to return to a classical continuous description. But again, the hope was deceptive. Nature herself seemed to reject continuous description. I skip this one and I read the last line here. It is better to regard a particle not as a permanent entity, but as its instantaneous event. This is Schrödinger, okay? Not as a evolving wave function, but as a sequence, they should have better say, of instantaneous event when the particle interact with something else. The counter argument is that, but come on, the wave function is so visible, so intuitive, it gives us a picture of what happened. This is true. And of course, we should use the wave function. But remember, it is a wave function describing different atoms, orbitals in chemistry. But what gives us a representation of things should not be taken too seriously ontologically, otherwise we get confused. So this is a prototypical example. This is a fantastic representation of the caloric heat. Okay, this is a picture of heat, but that doesn't mean that we should take heat as an entity by itself. We know that heat is just a motion of molecules, right? And getting out of this realistic interpretation of what heat is what took out from the confusion about thermodynamics and statistical mechanics. And in the same spirit, stop thinking of the wave function directly with an ontological interpretation will help us. This is Bruno De Finete, who is talking about the similar things, abandoning the superficial credences about the reality of the caloric fluid, the cosmic ether, absolute space and time, or fairies and witches has been a step along the construction of scientific thinking. And I would add the wave function. And De Finete is talking about probabilities here, right? Of course, what you want to get rid of is probability. He's the main defender of the subjective interpretation of probability. And wave function is probabilities. It's just our expectation of what's going to happen next. And in fact, the wave function of a system depends on which other is relative to other system, depend what other system sort of knows about the system. Does this mean that giving an ontological way, I go back to the general philosophical issue here. Does this mean that giving an ontological way to the wave function is wrong? Well, it's not wrong. It's just not useful. Is that not the scientifically convenient things to be doing? I don't think science is about finding out what's right or wrong, reading the mind of God, finding the truth with a T. Science is about devising the most productive conceptualization at our present level of knowledge for understanding the world. I mean, I think that, you know, Howard Stein was particularly clear on that. And the talk, because before mine had a similar point, concept must come after knowledge, not before knowledge. A priori analysis of concept is misleading when the concept is based on wrong knowledge. We should understand something. If we happen to understand something, we just discover the world as quantum aspects, we should readapt our concept to the world, not in a rigid way, but not in a way that you can read directly out of the empirical information, because of what Feynman did. Nature can be looked at different ways, like human relations can be described in different ways. You can read Kafka and have 6 different versions of the same events. But some take us ahead and give us a wider idea. So views like many world and the hidden variables, pilot waves, they're not wrong, they're right. but they add concept. They forbid to take on board what seems to me the main message of quantum mechanics, which is that the old strongly realistic conceptualization of a continuous world is just not what nature prefers. So they add thing to case nature into our old conceptual scheme instead of adapting our conceptual scheme to nature. I just want to have one slide on the informational formulation of relational quantum mechanics, also because Lorenzo mentioned it in the introduction. One way of presenting all that is to use a language of information. It's one possibility. I don't want to say that the language of information is needed to make sense of quantum mechanics, but it does simplify. The risk is that information is such a slippery term that everybody wants to read what they want. Here is information is a very crude, deflationary, minimal term. It's sort of correlation between systems. So it's Shannon relative information, the technical version of the notion of information used. But in terms of this, the entire form of quantum mechanics can essentially be derived with some technicalities added from two postulates. One is the amount of available relative information about a finite system is finite. And second is that in spite of one, it's always possible to gather new relative information about any system. And quantum mechanics come from that, because you see, the key here is that 1 and 2 are not in contradiction because of this relevant information. So the relative information is the one that determines the probability distribution of what happened next. And what is being said here is that because of 1, there is discreteness. It follows directly. So there's a finite number of alternatives. This should be technically qualified. I'm not going into technicalities here. In how a system can affect another one. So the discrete of quantum mechanics follows. But even if you have maximal available information about a system, there's always a possibility to get new ones with some of the relevant information becoming relevant, some of the previous relative information becoming relevant. You measure spin in one direction, then you mean you spin in the other direction, the previous information becomes completely relevant. So from that, you derive uncertainty principle, pretty obviously. You derive the probabilities in quantum mechanics. And you see, this is about how systems interact. When two systems interact, the information that one system has about the other one, correlations, has these properties. And from that, the quantum mechanics come out. I don't want to go into that because it becomes very technical. Reconstruction theorems has been beautifully completed in a number of people. The most interesting version of me is the one quoted here. All right. So this is, I'm getting to the end because I look forward for a discussion and comments for all of you and your reactions. This is again a picture of the sixth version I had, where I've organized, I could organize this way, the sort of Bohr-like and the Einstein-like views, more inclined toward instrumentalism. And the problem was the problem of instrumentalism. I think it's scientific and philosophical. It doesn't tell us how to think about nature, and that's what we want from science. It only tells us about what we think. While Einstein insisted for a strong realism, these are all interpretations of strong realism, and but there's a compromise between the two. I mean, you can navigate between the radical between CILEM Charybdis, between radical instrumentalism and a realism at the price of inflation ontology, and that's what relational quantum mechanics does. So if it takes quantum mechanics as it is, as a realist theory, but not about the wave function with all the camps, as a realist theory about interaction between systems, but it's a slightly sort of weakened realism, like, velocity, position, as they define classical mechanics by Copernicus and Newton and Copernicus are weakened with respect to absolute position, absolute velocity known in classical mechanics. So you give up some strong realism, accepting that physical variables are about relations, not about things. To navigate between stay away from radical instrumentalists, have the possibility of thinking what happened in nature without adding an excessive, useless ontological weight. So that's my take about quantum mechanics. This is the main message. If you want to make sense of quantum mechanics, stop thinking of the wave function as the thing we're talking about. Just think of it as a tool for calculation of what actually happened. But what actually happened is real, but it's relational. And I close with a slide, which I just leave here. This is my book in which this is discussed much more in details. And these are the main paper of relational quantum mechanics. And this is a number of philosophers who have sort of framed quantum mechanics in the context of different philosophical or programs, if you want, or views. Quantum mechanics, relational quantum mechanics is not a philosophical position. It can be read within different philosophical positions. I know, Van Frassen, constructive empiricism, structural realism, this is what Dorato and Cadiotto do, even Kantian perspective, this is what Bitbull does. It's quantum mechanics is sort of, relational quantum mechanics is philosophically informed, or try to be philosophically informed way of addressing an issue in the interpretation of current physics, which I think it's beautifully open, and it try to take us ahead. So I stop here. Thank you very much. I spoke 50 minutes, and I look forward. I do hear, unlike Casey before, so I look forward for your comment, criticism, and to learn.
Thank you very much, Professor Rovelli, for your excellent talk. Professor Lorenzo Boccafoli is having some trouble with his internet connection, so I will be in charge of the Q&A. I posted the rules in the chat, so same as before, if you want to ask a question to Professor Rovelli, please write me down a private message and I will give you the word in order. So the first one is Sebastian Hill, so I will now give the word to him. Sebastian, do you hear us?
Yes, sorry, I just had to move down turn on my microphone. Yeah, so Carlo, thank you so much for the talk. It was very illuminating. I got a lot out of that. So my question is kind of a procedural one, and it has two directions. So first of all, if we're interested in going beyond non-relativistic quantum mechanics and actually wanting to go into some of the open problems of quantum gravity, how does relational quantum mechanics help us? And in particular, I'm curious to how we can adopt this viewpoint into making sense of what we would call the atoms of space in some kind of pre-quantized or quantizable manifold that we would deal with in quantum gravity. So thanks.
Yeah, thank you for this question. Yes, I've not mentioned that, but this is the reason I've been pushed toward relational quantum mechanics, quantum gravity, as I said at the beginning. I have two answers. The first is that there is a deep relationalism in general relativity. In fact, even the name was chosen by Einstein about relativity. And the relationalism of general relativity, our best conceptualization of space-time today, regards localization, where things are. And one can also use the name systems in general relativity. A system is something which is sort of localized in space and also in time. It's easier to think something's positioned. So a process, if you want. A process is happening somewhere, some region, compact, from an initial time and a final time. And the point is that this talks very well with relational quantum mechanics, because in relational quantum mechanics, the first thing you have to do is to take the world and break it in pieces, okay, and say how one piece affects the other one. And what are these pieces? Well, generative is telling us, look, the pieces don't live in space-time. They are space-time. They connect one with the other by space-time boundaries. So this opens the possibility to identifying the boundary of a region with the Heisenberg cut, the separation between the system and the other system in the interaction. And this works bingo in quantum gravity. That's what we need in quantum gravity, because we're describing what happened in some space-time region from the outside, so to say, how it affects the outside. So this is because of locality, right? Interactions are local. In physics, all interactions are local. So to be next to one another is the same as to interact. And so in quantum mechanics, in quantum gravity, marvelously, the who is next to whom and who interacts become the same thing. So that's a beautiful way of thinking about quantum gravity. Quantum gravity is not about things seen from outside. It's about how space-time acts on the next piece of space-time. That's the first answer. The second answer is because of this quanta of space that you very appropriately mentioned, right? If we think of the quanta of space as things, objects, which are just there, we get confused. How do we have to think about the quantum space? We have to think like the photons. A photon is not an object, it's a mode of interaction of the electromagnetic field with a screen, right? The electromagnetic field generically is not made by photons, it's a quantum superposition of photons, which is a very different thing for a philosopher, right? It's not just 10 photons or 5 photons, it's both. So it's not made of photons in a naive, mereological, classical, simple-minded things. Is that the electromagnetic field is something, the electromagnetic field in a box is an entity which interacts with whatever interact with it by exchanging energy in packets. And that's what a photon is. So the quanta of space are the mode in which the gravitational field interacts with anything else, with a clock, with matter, with me, with another piece of the gravitational field. So to do quantum gravity, one has to have clarity about quantum and clarity about space-time. And I think that the relational view permits that, because we can always describe, take a quantum gravitational phenomenon, whatever you want, a black hole ending its evaporation, doing quantum gravity and exploding in some manner. Good. So you encapsulate this, you call it a system, you encapsulate it in a region, and you say, quantum mechanics gives the probability amplitudes of what happens before to what happened next. So how this is interacting with something before and how is it interacting with something next. I've been a bit fast here. It's a work of my life, but I think I've given the feeling of why I think this is a useful way of doing quantum gravity.
Okay, so thank you very much. Now the next in line is Diana HB or Diana HB. So you can now proceed.
Thank you, Diana. Sí. Well, first of all, thank you so much for your exposition. I'm very glad I found this event. I come not from the philosophy formation, so it's fascinating for me. I wanted to ask about what is your opinion about feminist epistemology of physics? Because that I heard about you through that area of knowledge. So I wanted to know what was your position about that, that kind of knowledge or theories, and if you find it related to your work. Thank you.
Thank you, Diana, not Diana, Diana. Thank you very much. Now, I'm going to give an answer that probably is going to surprise many people who listen, because you would expect a hardcore scientist like me, a a physicalist, a naturalist, a scientist, in the sense to say, oh, I have nothing to do with feminist epistemology, or a comment like that. It's a way of thinking that comes from a very different traditions. But in fact, I'm going to use a completely different answer, the opposite answer. I am not an expert, but I have some knowledge about feminist epistemology. I've been curious. I've been exposed to something. I've read some book, for instance, Barad, who talks about quantum mechanics. She uses ideas of Bohr's and sort of re-employ them in her work about feminist epistemology. And I find all that extraordinarily fascinating and useful also for a physicist, for a number of reasons. Because feminist, let me just say some simple thing. One thing is that feminist epistemology is insisting that when we talk about our knowledge, we should not forget who is talking and the subject sort of the, and this seems to go against the sort of the traditional idea of what science is, but I think it's not at all. I think that a lot of modern science has gone exactly in the direction of realizing that the world we are describing is a world in which we are immersed, and that we describe from the inside, not from the outside. And in fact, quantum mechanics is it's a center, perhaps, of that. Even if it is already in relativity, it's already another part of physics. But in quantum mechanics, it's very strong. Quantum mechanics describe how a system interacts on another system. And if you want to see this from the outside, you're actually missing what is going in. You don't have a more complete view. You have an incomplete view because properties are relative, because what I said. So in the case of the Schrödinger cat, the cat observes something, and this is a piece of reality. If you describe it from the perspective of, Wigner aside the box, you're just missing what is going on entirely. So I find that this insistence on viewing the world from the inside, of viewing the knowledge as a part of our, so interpreting our knowledge of being knowledge of one piece of nature with respect to another one, and therefore characterizing everything we know in terms of everything we say, in fact, in terms of who we're saying. It's very deep, and it totally resonates with the kind of physics that I've been doing. So I was fascinated by reading Barrett, for instance, and other similar ideas. Again, I'm not an expert, so don't take what I say too much on the golden. But I think that there should be more dialogue. Of course, a lot of feminist epistemology comes from a very different quarters of philosophical thinking. I mean, most of the philosophers I talk about are in the strict analytical, traditional, philosophy of physics, Pittsburgh, London, Ontario, and so on. So Van Frassen and company. So it's a different universe, and it takes time to and between these universes there are incredible misunderstandings. They picture one another as totally idiots sometimes because there's a deep misunderstanding of what is being said on the other side. There's much more in common and the possibility of learning than what looks the first time. So I am looking forward for learning more, in fact, about feminist epistemology.
Thank you.
Okay, thank you very much. Next in line would be Professor Graham Priest. So please, you can now proceed.
Thank you. That was a fascinating talk. I confess I'd never heard of the relational view of quantum mechanics before. I don't know a great deal about this area. So these questions are very much an amateur's, and so take that into account. I can see the attraction of the relational view because there's a certain sense in which it deprivileges the observer. The observer is just one more part of our apparatus. Okay, and that That's good. But I wonder if the problem hasn't just been pushed somewhere else. Because, and the crucial thing is how you interpret the wave function. Okay. Now, you described it as epistemic or epistemological, and that could mean of various things. We might have to say more about this, but suppose you understand that in the most flat-footed way, namely it's to do with knowledge or a knower. The status of a privileged knower seems to come back into the picture. Who is the we that's knowing? Okay. And maybe one way of kind of bringing this problem home is something like this. Suppose that cognition had never evolved in the cosmos, thought experiment. Then it seems natural to suppose that the cosmos, or bits of it, would have continued to evolve by the time-dependent Schrödinger equation, even though there's no cognitive agent. And that tends to suggest that the wave function is not simply epistemic, simply because there are no knowers. Okay, so that was an immediate thought.
Yeah, thank you. This goes to the core of the point. So let me try to answer step by step to what you said, and but I look forward to your reaction to all that. So the first thing you said is that it's the first time you encounter relational quantum mechanics. I'm not surprised. It's relational quantum mechanics is quite old. Was born in the 90s, but the reaction to it has been very slow. And the interest of it has been growing. It was minimal at the beginning. And in fact, in spite of coming from the physicists, the philosophers who picked up first. Van Frassen is one of the first who reacted to that. And I would say it's in the last years or few years, the last decades maybe, that the interest in knowing. Now there are workshops and conferences. So now, correctly you say it's an effort to jump out of the apparent subjective aspect, and let me put it more sharply. It's replacing subjectivity with relationalism, which is obviously a completely different things, but it's an easy misunderstanding, especially in talking about physics. And let me make this example. In physics, when we talk about special relativity, nothing to do with quantum mechanics, we always use, or even Galilean relativity, we always use the word observer, right? We say the velocity depends on the observer. So if you're on a train and on the ground, you attribute different velocities to things. And in fact, when you say that something has a velocity, you have to say with respect to which observer. Okay, so it's my favorite example. When a mother says to the kid on the train, "Don't move," she does not mean jump out of the train and don't move with respect to the earth. She means don't move with respect to the train. Now, this language seems to be saying that velocity is subjective, because it depends on the observer. But of course, velocity is not subjective. It's just a bad language used by physicists. Velocity is relational. The moon has a velocity with respect to the Earth, has a velocity with respect to the sun, has a velocity with respect to the galaxy in current physics, but not because the sun has any knowledge of the moon. The sun doesn't need to have to be a subject of knowledge for the moon to have a velocity with respect to the sun different than and so on and so forth. So there are relative velocities on a different galaxy where there is nobody to talk about that. Now, once this is clear, and this is just what it is a clarification of terms, and don't confuse the apparent language about subjectivity used in physics with a relational one. Relational quantum mechanics say, look, we're doing the same mistake in quantum mechanics. We interpret it as subjective, something is just relational. Now, what about the wave function? My answer to you is forget the wave function. I mean, we can do entirely quantum mechanics without ever talking about the wave function. Just forget about it. And we can talk about facts, about events, about probabilities is a frequentist, so I'm not even subjectivist about probabilities. I mean, the same situations evolve repeated a large number of time, happen to be, P1 go in one way, P2 go different ways. So no knowledge, completely objective description of what happens. And quantum mechanics can be formulated in that way. So the relations between the probabilities are captured by transition amplitudes, which can be computed not as evolution of a wave function. And in fact, this is how quantum mechanics was formulated first by Born, and Heisenberg, and by Dirac. The wave function came later. Now, nobody forbids us to talk about wave function. So I can talk about the weather on Earth and be convinced that there was a weather on Earth before humans came, and have the conceptual structure for saying, before there were humans, it happens to be the fact that if there was sunny on California on a certain day, it was likely to be sunny with a certain probability on Arizona in the next day. Okay, so use a probabilistic language. But then we can say, what is the weather forecast? Or is our discussion about predictions about the future given the current knowledge? So given knowledge we have about some, so in that sense, if we talk about our knowledge, we code our knowledge in something which we call the wave function, and we code our expectations in something we call the wave function. But this is a tool we use for describing a set of real facts that happen in nature that, for reasons that we're not discussing here, happen to follow some probabilistic regularity among them. Is that an answer to your question?
Well, that's kind of interesting, but it seems to me that you're having it two ways, because you want to talk about an agent's probabilities and so on, so that the agent is still there in a sense. But then you said, well, we can forget it, and we can just think of them mathematics. Is it true that you can do quantum mechanics without the wave function? Yeah,
absolutely. I mean, just read the 95 three papers by Born, Jordan, and Heisenberg. There's entire quantum mechanics, and the wave function was not invented yet. It was invented a year later. But there's entire quantum mechanics. What happened is that the language is non-commutative algebras, matrices at the time, and the physicists didn't know it. So everybody jumped on Schrödinger formulation, which is differential equations that everybody likes and loves.
Okay, look, I didn't know that. That's interesting. But if that's right, I think it's kind of misleading to say that it has an epistemic interpretation.
Sorry.
Just get rid of the damn thing.
Yeah. Sorry. Before answering, let's do, a bit of epistemic, feminist epistemology here. Where are you talking from? What is your...
I'm a philosopher.
A philosopher, which band? which religion?
I'm a logician.
Oh, okay. So good. So I know what there might be also a little bit of a terminological misunderstanding here between us, because in the jargon of the philosophers who discuss the interpretation of quantum mechanics, it's common to divide the interpretations, calling them realist wave function or epistemic wave function, depending or not whether you assign an ontology to the wave function. So you call generically epistemic interpretation everything which doesn't take the wave function realistically. But I think listening to you, I realize that this is misleading, because what is being said here is not the wave function as an epistemic interpretation. It's just it doesn't have an interpretation. It's just a tool for doing calculation, which is not. It's a very different thing. It's, take classical mechanics. classical mechanics has an ontology which is completely clear. The non-relativistic quantum mechanics of a few particles subjected to forces. So you think there is space, there is time, and there are little balls going around pushed by forces. Fine, and that's clear. And then you say, oh, look, I can describe this using Hamilton-Jacobi theory, which is a function spread in time, and I take derivatives and I find the trajectories. Good. So what? Well, what is this function spread in time? It's a useful tool that we use for computing the trajectories.
Okay, no, I don't want to monopolize discussion, so I'll just say one more thing, then I'll shut up. That makes sense, but it makes it sound that you're taking an instrumentalist position. Okay, so then the question becomes, how does this view differ from just a simple instrumentalist view about quantum mechanics?
Because there's no mention about agency, about the observer, about the macroscopical world, about measurement. It's I will interpret nature as a set of facts, which are facts that happen when systems interact. And these are relative facts, which can be described, but they are facts associated to two systems. And the way these facts are related, which are the laws of physics, so to say, have to remember that facts are facts relative to systems. So if you, so this has to be taken into account into writing the analog of the equation of motions. And if we don't, we get confused.
Thank you.
Okay, thank you very much. Next in line will be Kasia Jaskov. So now you can proceed, please. Prof. Jaskov, we don't hear you. You are not with the...
Okay, thank you very much. I'm glad I'm next in queue because my question is also about the observer. But first of all, let me just say thank you for a wonderful talk. And my connection has improved, so I heard you. I fiddled with my computer during the break. And by the way, if any of you have any more questions about my talk, I'm happy to set up a session 20 minutes or so later on in the week and have a chat. But now, Carlo, yes, it's about the observer, because the way I look at it, I sort of I think, as I was saying in my talk, we all meta-represent what physicists are saying, but I think I understand that when you talk about breaking up reality differently, talking about it in the system, you can have different descriptions depending on which system you currently are. But I agree with the previous, with Graham, that you still have the observer, you are you. And when I look at what you are saying from the perspective of the observer and as a philosopher, I just wonder if it wouldn't be easier to get into all the nitty-gritty of physics if I questioned the ego, the me. Like in philosophy, there are these two schools. One is endurantism, one is perdurantism. One says that the ego exists fully and objects exist fully at any time. And the other, perdurantism, says that objects don't and we don't. We have temporal parts. There is no me. There are just different parts of me in different times. So if you want to get rid of the observer, wouldn't it be easier to just sort of philosophize like that? There is no me giving us this talk. There are different parts of me or different kind of configurations in these different systems you are talking about. And then I'll have this direct insight in what it is really like. So basically, that will be the way of getting rid of the observer. I just wonder what you think, if it's not the better way for us to get there.
Yes, Kasia, this is very interesting. In fact, in my book, I go into this discussion, my last book, Helgoland, on quantum mechanics or relational quantum mechanics. Let me not answer directly to your question, but answer indirectly by saying what I do in my book. In my book, I go the other direction around. In fact, in both my books, The Order of Time and also Helgoland, First of all, I think that thinking in terms of what you called the endurant, the permanence of the entity, is something that for a relativist like me, it becomes less and less comprehensible the more you study physics. I mean, there's just no sense whatsoever in it's a, you know, it's convenient to put together a wave on the sea at some time and the wave of the sea on a later time and say it's the same wave. It's just a convenient. I think that you know, Goodman put it. An object is a monotonous process. It's a process that doesn't change much. But I go stronger in the in Helgoland, namely, I think that quantum mechanics is pushing us also to consider the subject just as a convenient naming of a composite process, a composite set of processes that all together imprecisely make what I call myself. If you want, in the direction of a Buddhist, there's no self. I mean, self is depending on something else as heavily. Now, what I'm trying to say here is that the entire emphasis of relational quantum mechanics is that the best account that we have about reality, including ourselves, from physics, is that there is a world, and this world can be described by arbitrarily breaking it in pieces. For instance, I can say this pen and talk about this pen. This pen has some properties. It's green, it's oriented in this way, and so on. But I can also break this pen in two or in many, many atoms and describe the property of the atoms. There are many, many other properties which are not pen properties, but they're atom properties. In which sense precisely? The property of this pen are not property of this pen, are property of the way this pen interact with another object, with my telephone, or with my eyes, or with my brain, okay? And so the pen has a number of ways of interacting with my brains or with the telephone, and there's absolutely no difference between my brain and the telephones from the point of view of physics. There are all sorts of differences for me, of course. There are all sorts of biological complexities in my brain, which are not in the telephone, but not from the point of view of physics. So I can describe correlations between the telephone and the pen. They have interacted, so they're both oriented in the same manner. Okay, and this has sent a photon to me. So in my neurons, there was something correlated to the pen. Okay, in that sense, and only in that sense, I talk about relative information the systems have about one another. Carefully, I'm not doing psychology here. I'm not doing brain science here. I'm doing physics. But I hope, I expect, on the basis of this physics, that brain scientists and psychologists give me a story about the rest. So the subject of knowledge here, it's considered to be a piece of the world, but only described from the point of view of physics. I'm not describing my own views of the world. I'm just doing the same job as if I, as a physicist, was looking at a photographic camera and saying, look, inside there's a picture which actually corresponded what there's a correlation between the picture and outside, and I see that there is correlation that is established, period.
Yeah, but I just wonder if you are talking to philosophers, psychologists, if it's not easier to actually start with that. There is no ego, there is no self, and if you start with this perdurantism, as we call it, then you as an observer become sort of part of what is the lack of observer. So it makes this contrast disappear, because you think from the perspective of the self, which doesn't exist. It's just, sorry, it's not my area, but neither endurantism nor quantum physics. It's just, it seems to me that it's easier to comprehend it then.
I get it. Thanks.
Okay, thank you very much. Now we will proceed with the question of Santiago Núñez Corrales. So you have the word now.
Thank you so much. Thank you, Professor Rovelli. I had one question listening to your talk, and it is, in which ways or whether it is possible using relational quantum mechanics to gain better insights into things like the correspondence principle and more generally on both the philosophical and physical aspects of emergence, especially the emergence of new laws in the universe. Thank you so much.
Thank you, Santiago. The debate about emergence, it's rich, right? I think relational quantum mechanics can only say something about the specific emergence, that it's emergence of the classical world from a quantum world, if you want, which is quite a remarkable piece of emergence, but it's just that. And of course, the first formulation of that, it's more correspondence principle, which you refer to, which was not only a formulation of an expectation about emergence from quantum to classical, but also a key tool for more to devise what quantum theory should have been in a period in which everybody's feeling was we don't have a quantum theory yet. Before 1925, we don't have the quantum theory yet. Let's say everything which this theory should do in order to be good. It should do this, this, and that, and in particular should obey the correspondence principle. Now, in relational quantum mechanics, there is a technical piece of world which is the definition of stable facts, which I don't go into the details here, but I hinted about it in my talk, which is the description of how the classical world emerges. And concretely, what happens is that you start from these properties which are relative. So the pen is it's an orientation sort of relative to is here relative to the phone, but then they call this relative facts. But then you do some calculation and you realize that when there are many degrees of freedom around, you don't need to use the relative facts anymore. You can just forget who is relative to who, and the predictions don't change. And you know exactly what are the conditions for this to happen, and these are the conditions for essentially there are many degrees of freedom around interacting, which is what the classical world, what makes the classical world. So one sees clearly how you have an emergent description by disregarding something, which is what we do regularly in our life. So what kind of emergence is that? It's emergence in the weakest possible sense. When you have levels of description, like we always have, we use in nature, if you interact with many degrees of freedom or sort of less degrees of freedom in some context, there are concepts which are extremely useful and fruitful and effective at some level, which only make sense under this approximation and in these conditions and disregarding the degrees of freedom. And so you can make a story at this level, which of course it wouldn't make sense in general at the bottom level, but it makes perfectly sense at this level. And we call this emergence. Okay, so this is how interpret emergence in physics. We see all over physics, and in fact it leads to me to the idea that we better think that each level of description is sort of a level of autonomy. We don't need to think of the bottom one as fundamental. That's my own view of this thing. We don't know what the fundamental one, but we have a good understanding of the coherence between different levels in terms of emergence in this sense.
Thank you so much. One of the follow-up questions would be relatively to the, or relative to the definition of degree of freedom, then can you expand upon that to really unravel what that specific term means, or under this sort of view? Because degree of freedom usually means a variable that can be assigned within a certain range in the physical sciences, but whether one can ascribe a different meaning under this relativistic interpretation.
Okay, so degree of freedom is a very technical notion in physics, widely used, and there is a subtlety in it. So what is a degree of freedom? It's a counting of how many variables we use to describe a system. So if I have this pen and I don't just consider it as a pen that can move and I cannot break or do anything else, I can give its position in the X direction, the Y direction, the Z direction, and its orientation in around two angles, and that's it. So I have 5 numbers that that characterize everything I can say about this pen, and so I say that this has 5 degrees of freedom. This is what we do in physics. Now, the subtle thing, of course, is that this pertains to a description of this pen under some conditions. Okay, if I break it in 2 pieces, then I have more degrees of freedom because the 2 parts move independently. And if I look at how the single molecules move, I have many more degrees of freedom because I need many more numbers to describe it. So the notion of number of degrees of freedom, it's universal in physics. I mean, you studied first year as it was, something absolutely fixed about systems. But of course, in real systems, it's badly defined because it depends how you're interacting with the system, right? I mean, this if I pull and push them, this pen, I can give a description of its dynamic with these 5 degrees of freedom. But if I pull too much, I have more degrees of freedom because it opens up. And in fact, in quantum field theory, this is very obvious. I mean, the number of particles changes the more I put energy, so the number of degrees of freedom grows. So it's subtle as a notion because it is not really, once more, it's not really a description of the system by itself. It's a description of the ways the system can interact with the rest, the number of variables in the way the system is interacting with the rest under some conditions. There's not too much energy, or the physicist would say you don't excite other hidden degrees of freedom. Is that part of an answer?
Yes, it is.
Okay.
Thank you so much.
Thank you very much. Now we will proceed with the next question. That is, in the case of Milena Castro. You have the word now. Please ask your question.
Thank you. Thank you. Can you hear me well?
Yes, Milena, very well.
Thank you. I'm really, really happy for listening to you on this opportunity. I try to be very, very synthetic, but I have many, many questions. Probably I would like to write to you later on or something like that.
Please do. Please do.
Thank you. I'm a biostatistician here in Costa Rica, and I'm been dragging a lot about, well, there are many things that it's been lighting up my ideas. So one of the things that you said is specifically in the empirical characteristic of a question, of a research question. And the way I like to see this is all of my papers and my models, I really, really insist in that we have to undertake like three different processes, which is a specification of the model. The second will be the estimation process, and the third one will be the interpretation of the model that you are proposing to explain whatever phenomena you are looking at. But having that, you have said, let's take the wave function out. And so my question will be, which models will you propose in order to undertake the estimation part specifically? Because that looks like it's kind of the thing that everybody likes the most, and how you define a probability is very, very, and I will say, I wouldn't say subjective at this talk, I will say relational to who you are. So that how will you undertake this estimation process, but also adding this philosophical part or this discussion, especially when you define the variables. And it is actually funny that you are talking about degrees of freedom. I will actually ask if this is staying with the frequentist statistical issues or parts, or how will you interpret this in the Bayesian context, if that is meaningful for you? Thank you very much. I have many other questions, but I will start with this.
Okay, let me understand better. I understand the question about probability that you put at the end. When you say estimation, do you mean how to sort of confirm, evaluate, and then support the theory I have? Is that what you mean? Is that...
Yeah, like this is basically what everybody likes. It's like everybody is, I think it's more the positive way of looking at science. And if I understood your talk well, maybe it's expanding this idea, and maybe, and you have actually demonstrated in the degrees of freedom talk or answer, is that you define a model with certain parameters, but not all the parameters are inside that, because not all of the observations that you can actually observe are considered in the model. And so
okay, so okay, let me try to answer in pieces. You tell me, Milena, if I am answering or not, or if I'm going. Let me answer in three steps. The first is more general. The second is about quantum mechanics, and the third is about probability. So first of all, this point, quantum mechanics is a strange theory because it's not a specific theory of something, right? It's a general structure of doing mechanics within which you write specific theories. So quantum theory is like classical mechanics. It's just, the rule of the game of physics, so to say. And then in the context of quantum mechanics, you do the quantum mechanics of an atom, the quantum mechanics of a free particle, the quantum mechanics of the molecule, the quantum mechanics of the interaction on the sun, the quantum mechanics of the universe, and each one of these is a theory. So the big step in the discovery of quantum mechanics is the way you have to play these games is not as in classical mechanics attributing values at every moment to variables, but in this strange way of probabilities when there is an interaction. This, I think, has to be put forward because one thing is evaluating, in your sense, quantum mechanics as a whole, and one thing is evaluating the single theories between quantum mechanics. Like QED, for instance, is a theory formulated in the context of quantum mechanics, and we evaluate it. So this is just as a preliminary step. Now, for a scientist like me, who is not perhaps, I mean, super interested in philosophy, but I'm not a philosopher. In the actual practice of science, you constantly do with data interpreted already within a scheme that are less in accord with the predictions of the theory. So the theory gives predictions. Predictions specific. I mean, you take an uranium, and the theory tells you that after a certain time, with high probability, it will have decayed, and then you check it, and you can do it remarkably even in phenomena that you haven't checked before. So you have theories which are strongly predictive about numbers, but always strongly predictive about new phenomena, even more. Right? Entanglement was predicted before even thinking of measuring it. So nobody thought that there could be anything like entanglement. The theory says, look, if you measure that and that, you will find this strange thing, and so on. So my view in this perspective is Bayesian, strongly, namely, to the extent in which the predictions are confirmed, our degree of confidence in the theory goes up. And to the extent in which it's not confirmed, I think Popper put it too strongly, our confidence theory goes down. I mean, of course, we don't think a theory is wrong just because it gives a wrong prediction. We think that we're missing something. We fake around. We do something. But at some point, if enough things go wrong, you say, no, wait a minute, this is not working anymore. So it's Bayesian. We have a machine for a mathematical machine for predicting. We collect, we continue collect information, and we check it, and the things go. The credibility of the theory goes up and down. Of course, this is complex because the interpretation of data already, as we know very well, requires a huge amount of theoretical pieces. So we never know what exactly we are questioning. You know, like Quine has emphasized, when we're evaluating a theory, we don't know, are we evaluating the theory or the other theory which we've granted around it, or it's largely everything inside. So in that sense, it's a Bayesian view of confirmation, but not strict, because we never know exactly what we are confirming and not confirming. So this is the general attitude. And of course, I think that, you know, a good philosophy should close epistemic circles, as Shimoni would say. So this entire phenomenon should be comprehensible within the theory itself. And that's why I like the relational aspect of quantum mechanics, right? Because we are not doing that as, you know, outside nature, getting data. We're doing it as pieces of nature which interact with the rest and collect information about the rest. So we collecting data can be described by the theory itself. Now, in all this, how do I think about probability? Because of course, all that is probabilistic. It's not yes and no. It's never yes and no. It's a probabilistic already in classical physics, but it's even dramatically probabilistic in quantum mechanics, which I think tell us that we have to be probabilistic. It's no determinism. So the best is think probability. Now, what we mean by probability, it's one of the hardest questions, and I don't dare going into it. I'm reading a book by Wayne Marrell on the interpretation of chance and probability. So every 3 pages, I change my mind of what I mean by probability. I am still tentatively Bayesian, Definitian, subjectivist in thinking about the use we do of probability in our everyday life, including in interpreting and evaluating theories. Namely, what we're really doing is expressing our confidence. What would we bet if we had to bet? Something like that. I mean, that's what we mean by probability. But whether behind that, I want to think that there is a stronger objective sense of probability in the world, which might be useful for, I don't want to commit myself neither to yes or no. And, you know, I listen carefully and with enormous attention to the people who think about that better than me. You know, like all physicists, I'm a frequentist when in the many cases in which being a frequency works so well. But I'm aware that I talk about probability in cases in which frequentist doesn't work. So I'm aware that, you know, probability is more than being a frequentist, and so on and so forth.